So this is the final, I'm getting a little burnt out here because I've been doing integration all day, and you're probably burnt out because you've been doing integration for 2 weeks. Good night. But this is the last technique of integration that we're going to talk about, and it's called partial fractions. So the idea basically is that if you have something like this, so ax plus b, that this can be written as a times x minus d plus b times x minus c. If we multiply this out, we would get ax minus ad plus bx minus bc. And so this is a plus b times x minus ad minus bc. So if a plus b is equal to a, then the coefficient of x is the same. And if little b is equal to negative ad minus bc, then these two are equal. And if this is true, then basically this is true. A to the x plus b over x minus d times x minus c is equal to a over x minus c plus b over x minus d. Now that's a step, I'm sorry that wasn't in the frame, but that's a step that maybe doesn't make complete sense. But remember, really what we're doing is we're taking this whole equation and we're multiplying by 1 over x minus d times x minus c. So here we get the x minus d, x minus c. When you multiply this by 1 over x minus d times x minus c, the x minus d's divide. And this one, we multiply and the x minus c's divide. And so this is true. So basically what we're looking at here is this is something that's hard to integrate because it's linear over quadratic. And that's not nice unless this happens to be the derivative of this or a multiple. But these are easy to anti-differentiate because these are just natural logs, right? This is just natural log of x minus c times a and natural log of x minus d times b. So basically the idea is that if we can break this up like this, we can simplify some integrals. And this is called partial fraction. This is partial fraction decomposition, but we're going to use that to integrate. All right, so let's take, for an example, this right here. All right, so the example is antiderivative of 1 over x minus 2 times x plus 5 dx. Now this is 1 over a quadratic, so this is no good with u substitution or integration by parts or anything else. It's just nasty. But what we might be able to do is, could we write this, okay, question mark, as the antiderivative of a over x minus 2 plus the antiderivative of b over x plus 5. So if we could find some constants that make this true, then we know how to anti-differentiate this and this because that's just going to be natural log. So we're going to start by saying, look, let's let 1 over x minus 2 times x plus 5 be equal to a over x minus 2 plus b over x plus 5. And now we don't like fractions, so we're going to multiply by the least common multiple of the denominator, and that is simply x minus 2 times x plus 5, because these factors are already contained within this one. So when I multiply everything by x minus 2 times x plus 5, this becomes 1. This becomes a times x plus 5, and this becomes b times x minus 2. Again, here the x plus 5's divide, here the x minus 2's divide, and here both of them divide because I'm multiplying everything by x minus 2 times x plus 5. Okay, now simplifying, I get 1 equals ax plus 5a plus bx minus 2b. And so 1 is equal to a plus b times x plus 5a minus 2b. Now, a couple things I know in this case, because really what I'm trying to do is find a and b. What I know is that right here is a 0x. Right? There's no x term over here. So if there is an x term over here, they're not equal. The only way they could be equal is if these are equal, if the coefficients of x are equal, which means that 0 has to equal a plus b. And if these are going to be equal, then the constants have to be equal. So that means that 1 has to be equal to 5a minus 2b. And that's nice because now I have two equations, two variables, and I should be able to solve using substitution or elimination. So let's review our steps. We had something that looks like partial fraction decomposition because it's linear over quadratic, or even in this case constant over quadratic, or something like that. It looks like a rational function. We set it equal to a over one factor plus b over the other factor because we know how to anti-differentiate these if we can find those constants a and b. We multiplied everything by the least common multiple of the denominator, and we ended up with this equation. Then we recognized, after multiplying out, that the coefficient of x has to equal the coefficient of x, and the constant has to equal the constant. And thus, 0 has to equal a plus b, and 1 has to equal 5a minus 2b. So, with that in mind, we can now say that a is equal to negative b from this equation. So 1 equals negative 5b minus 2b. So 1 equals negative 7b, so negative 1/7 equals b. And a is equal to 1/7. So we've just shown that the integral of 1 over x minus 2 times x plus 5 dx is equal to the integral of 1/7 over x minus 2 dx minus the integral of 1/7 over x plus 5 dx. Because going back to what we had before, this is a over x minus 2, and this is b over x plus 5. Now that's actually a big deal, because we could even pull out the 1/7 if we want to, and say that this is equal to 1/7 antiderivative of 1 over x minus 2 dx minus 1/7 antiderivative 1 over x plus 5 dx. And that's simply 1/7 natural log absolute x minus 2 minus 1/7 natural log absolute x plus 5 plus c, because those are the antiderivatives. And if I really wanted to, I could say that is 1/7 times the natural log of x minus 2 over x plus 5. That's using the quotient property of logarithms. Subtract 2, you can make it into a quotient. So, oh my goodness, what a problem, right? Let's go back here to the very beginning and remind ourselves that we had this. We think it might be equal to this. So we set them equal to say, can we find a and b such as this is true? We multiplied by the least common multiple of the denominator. We know that the coefficients of x and the constant terms have to be equal. That gives us two equations for a and b. We were able to find a as 1/7 and b as negative 1/7 and write this integral as the sum of two integrals we know how to find the antiderivative of, and then we simply antidifferentiated. So from here on is review. And really it's just a bunch of algebra that you kind of have to believe, but you could check that to see if you believe. All right, let's try another example. Let's try this example. Antiderivative of x plus 2 divided by x squared plus x dx. Now, the derivative of x squared plus x is 2x plus 1, which is almost a multiple of that, but it's not. So we're going to have to see if we can use partial fractions here, because this is just not going to work otherwise. So what we can do is basically say, first of all, that this is the antiderivative of x plus 2 divided by x times x plus 1. So we need these factors so we can then break it up. And so what we're going to say is, you know what? X plus 2 divided by x times x plus 1 is hopefully equal to some constant over x plus some constant over x plus 1. That's what we want, because we don't know how to antidifferentiate this, but we do know how to antidifferentiate these. Okay? If you had another factor, you would say plus c over x plus 5, right? If you had 4 factors, you'd have to have 4 different fractions here, because these are what we know how to antidifferentiate. Now, multiplying by the least common denominator, we should be multiplying by x times x plus 1. We should get that x plus 2 is equal to a times x plus 1 plus bx. Excuse me. And that means that x plus 2 is equal to a plus b times x, ax, bx, a plus b times x, plus a. So you'll notice that what I'm doing is writing this in x plus 2, something times x plus a constant. So now I can basically see what needs to be equal. So I can basically say, you know what? A plus b needs to equal 1, because the coefficients of x need to be the same. And a needs to equal 2, because the constants need to be equal. Plugging in 2 plus b equals 1, b equals negative 1. So that tells me that the integral of x plus 2 divided by x squared plus x dx is actually equal to the integral of a over x, so that's 2 over x dx, plus the integral of b over x plus 1, negative 1 over x plus 1 dx. And that's simply 2 ln absolute x minus ln absolute x plus 1 plus c. And this is equal to ln absolute x squared minus ln absolute x plus 1 plus c. That's the power rule of logarithms. Multiplication becomes a power, which is now ln of x squared over x plus 1 plus c. So I can use the quotient property to write it in that way. So we'll see a few more examples, but that should be your introduction to partial fractions.